Okay, so let's start the next part of modeling. We're going to look at modeling with the application of inventory models. Some of this is going to be a review of what you did in 355, and some of it is going to be extending what we've already learned. And we're going to look at how we can manage a single inventory item. And we manage that inventory in the presence of uncertain demand and uncertain lead time. Okay, so conditions that we would anticipate in business. So we've already learned a bunch of these things. I'm going to go through some of these today. So if you haven't already, I will refer to these, and when you go home, make sure you understand what each one of these are. You'll see that you have two S's. A small s is a reorder point, so it's a trigger point. It's a level that triggers an order. And you have a capital S, which is an order up to level, which is going to determine how much we order from the current inventory position. Inventory position includes available inventory as well as inventory on order. Okay, so inventory that we have on hand in the facility, as well as inventory that we have already placed, or orders that all the inventory that we placed and is on order. We have the review period, which is the time between which every R periods we are going to look at the inventory. So we only look at the inventory after R periods. We don't look at the inventory continuously. We talk about other models where we look at the inventory continuously and we continuously review the inventory. And these are different notations that we're going to use to notate the various inventory variables, and you're already familiar with some of them. So I will talk about each one of these as we go along. So when we set inventory, we already know that we have to determine how important an item is, and we've looked at how we do that. This is just a review. And when we look at what policy should be used, we have to answer two questions: how much to order and when to order. And in answering these questions, as we know from our linear programming experience, these are how would you define? How would you identify these as a linear program? Where would these two questions fit in a linear program or in a mathematical program? So I'll give you a clue. The cost function is the objective function, right? Yeah? So where would these two fit in a mathematical program? When to order and how much to order? Exactly, the decision variable. So this is the decision variable because this is a decision. When do we order? How much do we order? It's a quantity, right? That's a decision variable. So this is a decision. These are two decision variables, and we're going to define these as decision variables when we do some mathematical programming. And then we have to minimize the cost function in order to answer these two questions. We'll have some constraints. Those constraints would be determined as service objectives. Service objectives including how much should we have on hand? What should our fill rate be? how often should we have a stock out? What did we learn in 355? Why is it important to have these service objectives? Why can't we just say, we don't want to ever have a stock out? It's reasonable, right? We should be able to set an inventory policy so that we never have a stock out. But why did we learn in 355 it's not reasonable to say that or reasonable to do that? We looked at those trade-offs, right? Those trade-off curves. What happens as our service objective gets closer to 100%? Our cost increases exponentially. Yeah? Remember we talked about a normal distribution of lead time demand? Go back to the definitions. Remember we defined this lead time demand? Remember how we said you look at it as a normal distribution? So because we look at it as a normal distribution and we want to satisfy every single unit of demand, and the normal distribution goes to infinity, as a result of which we want to satisfy all possible demand during lead time, then our service objective is going to require us to have an infinite amount of inventory, which is an infinite amount of cost, right? So that is why we need to have service objectives that constrain our problem and say this is how much we want to satisfy 99% of all customer demand, right? Or 99% of the time we don't want to have a stock out. So the first question, how important is an item? We do an ABC analysis. We all remember ABC analysis? Yeah, the Pareto analysis. So this is just a basic rundown. We can segment by sales, by demand. We can segment by the customer purchase patterns. What is the usage rate if you're talking about a manufacturing environment? What is the criticality of a product in terms of what is its impact if it's not available? So in this case, we can do a dollar impact. And then we create these logical groupings. Those are the A, B, and C items. Obviously, A items are the items you want to manage the most closely. B items are the fast-moving items that make up a large percentage of our dollar value, and C items are those ones that we have to decide whether we have to hold them. Most of the time, we centralize the inventory management. So, very quickly, the same example. I'm not going to go into the details. But A items make up 80% of the value. So here you have the SKUs. Here you have the price, annual demand in units. And what we're doing is we're just multiplying these two to give us an annual volume. That gives us an annual sales value. This is the total annual sales, and then this is the cumulative sales. And then we just take a percent of total sales of this cumulative sales, and we say this is 80%, then the next 95%, and then the rest are all C values. Okay? So that's the basic rundown. Now, Ty, I know you've not done this, so you're going to be a little bit lost, but if you have any questions, we can talk about it afterwards. Okay? So those of you who have not done 355, this is going to look like it's not going to look familiar, and we can deal with it later on. So just trust me, this is a methodology to determine what are your most important items to manage, and then what are your next most important, and then the items that you want to manage differently. And we'll talk about each one of those now. So, typically, and these are policies, inventory management policies, they are considered, this is considered a rule of thumb. Okay, so we're going to look at these different inventory policies of how much to order, of when to order, and how much to order each time. So, and I'll go through each one of these policies. And for A items, we say if we are doing a continuous review, that is, in other words, we have information systems available that is constantly keeping track of our inventory, right? Then we have a continuous review system, and then for A items, we'll use this inventory system, for B items, we'll use this. If we don't have an information system, or if our operation is such that we want to review, for example, with international importing, we review our inventory every week, because every week we place an order with our international vendor, and the vendor then ships it to us because every week we have sailings from the International Vendors Port. So for periodic review, these are the two policies that we use. All right? So what about C items? Sorry? They're not as important, so how would you manage those? So typically for C items, you're going to be using some sort of a manual system because you don't have too many of those in stock because they're not contributing to a significant portion of your sale. You want to use some sort of a manual system, and you want to use a manual system that is close to an SQ or an RS system, okay, to the B item system. And the way you do that is you visually see, because what about C items? C items are not moving quickly. B items and A items are moving very quickly, right? So you can't keep track of that inventory. Whereas C items, you're not selling as many. As a result of which, you can manually keep your eye and you can say, okay, let's do some sort of a Kanban system where we know you have all of these items, these are all C items. We can manually see when something is needed. If we have 3 stacks, when we have just 1 stack left, then we know we have to place an order, right? So visually, you can keep track of C item inventory. So that's typically how C item inventory is managed. So you use a manual system. Either the small SQ or the R big S system. So what are these systems that we are using, that we're talking about? So for each of these systems, I've broken it down into their name, what they're also known as, whether they're a review period or not, what is the review period, when do you place an order, how much you place an order, and some additional remarks. So if you talk about the continuous review system, or in this case, the order point, order quantity, it's also called a 2-bin system, because in a manufacturing environment, just like I said, you typically have 2 bins. When you have So one bin is what's known as your cycle stock. Okay, that's your cycle stock, and the second bin is your lead time demand and your safety stock. So your cycle stock is when I'm using my cycle stock for regular everyday operations. When I use up that one bin of cycle stock, then it triggers, and the second bin, the quantity in that second bin is at S quantity. So that's telling me when I have to order. Okay. So that's when your inventory position is equals to or less than whatever you have in the second bin, you place an order. Okay? So that, of course, now with information systems, we can actually keep track of using RFID and using barcodes exactly when we hit that S or when we are close to the S position, and as soon as we pass that S position, we trigger an order. How much to order? The order quantity can be determined in several different ways. One is we use the EOQ, okay, just the basic EOQ. The second one, we can use a mathematical program and we can find out what is the S, what is the Q for our customer service requirement. Okay, and we'll look at some examples of that. Now this system is very commonly used in manufacturing. It has very, very small errors when it comes to discrepancies between what your expected customer service is and what the real customer service is. And when you're comparing it to the periodic review system, which is again another very commonly used system, especially for retail and for service environments, it has less safety stock on average than your periodic review system. Okay. Now this one is the order point, order up to system. So now you have an order point here, which is the small s, but instead of having a fixed quantity, a fixed queue, you actually have an order quantity system. So an order up to system. So what happens is when your inventory either equals S or passes S, then the order quantity that is going to be placed is going to be determined by the difference between what your current inventory is and the S that is set. Okay? So in other words, what's happening is your order quantity is going to change each time. And in some environments that is a problem, because your suppliers don't want to have variable orders. They want to be able to plan in advance so that they can plan for a fixed order quantity each time. One, it helps transportation. Two, it helps scheduling production. Okay? Three, it helps scheduling all the things around the production, raw materials, manpower, etc. So this system is a little bit less popular. Also, to find an optimal for the SS system is very difficult. Okay? So again, it's the same as this. You trigger an order when your inventory position passes the small s, and the order quantity is the difference between your inventory position and your big S. And you're continuously reviewing, in other words, your big R is 0. So you're continuously looking at what your inventory position is. Yes?
So if you're waiting for the inventory to drop down to the little s,
yes,
and you're ordering up to the max level,
the S, big S, yeah.
Big S, wouldn't that be the same order quantity every time? You kind of just put S, please.
It depends, because now suppose I have one pallet between my inventory position, one pallet load between my inventory position and my current S.
So like if you went too far below
if a customer places a truckload, now I have 26 pallets, so now it goes all the way down by another 25 pallets, right? So now that all of a sudden, I've got a truckload that's leaving, so that's a problem. But that's a good point. So, in this case, so this is called a min-max system, and very often you hear retail stores use the min-max system to stock their shelves. For example, if you go to any grocery store, you'll see that there's a certain number of items on the shelf, right? So that's the maximum number of items that they can have on the shelf. Okay, and then you have the associates walking around the stores, or based upon their whatever that's their point of sales and the inventory interfaces, it might trigger an order if there's only one item or two items left on the shelf, right? Of course, that's not always very accurate, because customers will take an item and decide they don't want to have it, they want to use it and put it somewhere else, or not put it back at all, and so all those kinds of things can happen. But in general, this is typically how most retailers manage their on-shelf inventory. The RS system is again very simple. It's called the base stock model. Most retailers use it to manage their DCs. The period is usually more than one day, so one period. Okay, 1 day, 1 week. So it's more than one period, whatever that period might be, days or weeks or months, usually in days. And you order every hour units of time. You place an order. And what's the size of the order? Again, very similar to this. It's the difference between whatever inventory you have right now, inventory position you have right now, and what your order up to point is, your S. Typically, you have the highest carrying cost over here, because your safety stock is usually the highest. And very often it's used in a DC environment because it's very easy to schedule your work requirements around. Okay, it's very easy to schedule your work requirements in terms of, if I place it this time, I know my suppliers are going to ship to me at this particular time, and then I can manage my receiving operations at this time, or I can go and do cycle counts at this time. So that's typically why the base stock model is used. And then you have, of course, this RSS system, which is a hybrid of everything. And very few companies actually use this, because it's really hard to find a good optimal for this particular policy. But basically you're reviewing the order period, you're reviewing at a certain R periods, and only when you review, if your inventory position is less than or equal to the trigger point, the reorder point, will you place an order, and the order will be the difference of the inventory position in S. So this system is almost, I've never seen it used practically anywhere, but there are some places potentially that could be using it, and I'm just not aware of that. Okay, so let's take a look at some of these graphs over here. So this is where you have constant lead time and constant demand. Now let me see if I have some animations available. I might have some animations available that I can show you. So what happens is, with constant lead time and constant demand, you have an order of Q that is placed. You have an order of Q that is placed, and because demand is constant, with time, you're going to have a steady decline in your inventory. You're going to have a reorder point of S. As soon as it hits that reorder point, you're going to have an order Q that is placed, and your inventory position goes up again, and so on and so forth. And this is called the sawtooth diagram. Okay? So a sawtooth diagram is basically your inventory position going down until it hits the reorder point, until the reorder point is triggered, your Q is placed, and the inventory position goes up, and so on and so forth. So your cycle stop is half of your Q, and we've already seen that, right? Last year in 355, that's your cycle stop. That is how much inventory on average you have on hand. Like I said, that's your review period, and every time you review, every time you place an order, every time it triggers the S, then after a certain number of L periods, the order Q comes, and then your inventory position goes up again. So this becomes your safety stop right here, okay? Because this is what happens if your lead time changes and if your order takes longer to come, then you have the safety stop for this demand also to for the demand to be fulfilled from this safety stop. Now, of course, in this case, we have constant lead time, so the lead time is always going to be the same. So as we saw, the lead time is the same, and in this case, your order cycle is always going to be constant, L periods. So what happens when you have, let's go back here. So in this case, what would be the optimal safety stop that you want to keep on hand when you have constant demand and constant lead time? What is the optimal safety stop that you can keep on hand? So right now this is my safety stop, right? So I place an order this time at S. The order comes after L periods. The demand is constant. Your lead time is constant. So I know that my order is going to arrive exactly after this amount of demand, after these periods. Right? Because lead time and demand are constant. So do I need this safety stock? So my safety stock is 0, right, in this case? So in this case, my optimal safety stock is 0. When demand is constant, when lead time is constant, I don't need to have any safety stock. Does that make sense? All right, so let's look at what happens when you have demand and lead time that is not constant. So again, I place an order Q, and this is my inventory at time 0. I placed an order Q, and that is by, you can't see it over here very clearly. I was trying to see why it was not coming up. But there is another line that is shadowing this. It's a shame that you can't see it. Let me just go back to the other slide we showed you. Oh, here too you can't see it. Do you see it in your notes? Yeah? You can barely see it in the notes as well. Let me see if I can darken it a little bit. All right, let's see format. Okay. Let's see if that makes any difference. Okay, that's much better. So, I place an order of Q. This is the actual balance on hand that I have in the facility. This is my inventory position, because now what is the inventory position? It includes what I have in the facility as well as my Q, right? Place whatever order I have placed. Now, what you notice here is that the trigger point is right here, and the trigger point is for the inventory position. So as soon as my inventory position triggers another order will be placed. Okay? So I have two orders that are on hand, and those two orders, the first order will arrive at this point after L1 periods, and after that demand, and then my balance on hand in the facility is going to rise up to a certain point. Now this will continue again until the second order is received after L2 periods, because with a random lead time, we don't know when the orders are going to arrive. In the meantime, the inventory position has already triggered a second order, and you can see over here that demand is also not constant, because demand can either be increasing or decreasing. It can change dramatically between each order cycle. Some cases, demand is going to fall very dramatically, as a result of which you're going to have stockouts. You will have a stockout, and you will have a certain number of items that are back ordered. Again, the number of periods after which you get the order is going to change constantly, and The only time when your inventory position and your balance on hand is going to be equal is when you have no orders outstanding. When you have no orders outstanding, then your inventory position and your balance on hand is going to be equal. Okay? Because at that point, your inventory position does not have any orders that are outstanding. So this is what your sawtooth diagram, your inventory position, balance on hand diagram is going to look when you have uncertain lead time and uncertain demand. And finally, we have the review period, and you'll see that every R periods we're going to place an order. So at the beginning of R, now we place an order, and the order is going to be based upon what we have, the inventory position up to our S amount, our big S. And again, you can barely see the inventory position, but that's shadowing the balance on hand, and it's just going up to the order up to point. And again, the rate of demand and the lead times are going to be changing. All right, so let's go back and now understand how we can actually manage these inventories. So before I go, I wanted to point out something about order crossing. Over here, we assume that the order 1 is received before order 2, and order 2 is received before order 3, and so on. But sometimes, especially when you have lead times that are in 4 and 5 weeks' time, then if one order has a lead time of 5 weeks, and a week later you have another order that has a lead time of 3 weeks, then the second order is going to arrive before the first order arrives, right? As a result of which, what's going to happen is if that happens often enough, and especially in global supply chains, it can happen quite a lot, up to as high as 50% of the time, then you can see that your calculated inventory is inflated. So your safety stocks and your cycle stocks are greater than what you've calculated them. And that's something that you have to be careful about. Nobody's really found an answer to that. We're still working on this problem of order crossing. So the effect of order crossing is your safety stocks are inflated. Okay? So that's the answer to that. Okay, so let's switch gears a little bit and do some modeling now with some of the insights that we've gained from looking at these models. So the first thing that we have to do is we know what our decision variables are. Our decision variables are how much to order and when to order, right? We're all clear about that. Now, how much to order is usually Q, and when to order is usually S. So we have to determine the cost function as the objective function as a function of those two variables. We will define the cycle stock as the average on-hand inventory, which is your Q, right? Or Q by 2. Yes. Question. S determines how much. S determines when to order. Q determines how much to order. Yes.
When the inventory position, what is the inventory position the same as
balance on hand? The inventory position is the same as balance on hand when you don't have any orders outstanding. Because what is the definition of inventory position? Balance on hand plus orders outstanding. So we have Q, cycle stock, which is a function of Q. Our S, or reorder point, or big S, and our order up to point, is going to, our safety stock is going to be a function of either the small s or the big S, depending upon the policy that we use. And that's our safety stock. Our safety stock is, on average, how much stock that we have on hand when we receive an order. Okay? At the end of the, that is at the end of the order cycle. And the pipeline stock is going to be a function of our average demand as well as our average lead time. So our estimated total annual cost is going to be, and we've seen this already, sum of the ordering costs, our cycle stock costs, our safety stock costs, our pipeline stock costs, and we put that all together to get our estimated total annual cost. So, in order to calculate our estimated total annual cost, we have, as we've already learned in our last class, our definition of lead time, random variable, right? We all remember that? Lead time random variable, and it has an average of mu L and a standard deviation of sigma L. We have our random variable demand, and it has an average of mu D and sigma D. We have a random variable of X, which is our lead time demand, with an average of mu X and sigma X. We have mu X, which is our average of lead time demand, which is our average of lead time multiplied by average of demand. And we have our sigma X, which is this formula over here, which you already have, right? From 355, and you have it here in your notes. So the small s and your big S. So here I'm giving you a small s, but your big S as well is your mu X plus k times sigma X. And what is k? K is the standardized reorder point. In other words, you take your reorder point and you standardize it, assuming that your lead time demand is normal. And we look at some examples of that. Now, this thing is not coming very, very clearly for some reason. I don't know why it's doing that. But your S is the inverse CDF of your probability of not stocking out. So if you remember, your probability of not stocking out is your customer service objective, which is telling you how many order cycles do you not want to stock out of. So if you don't want to stock out 99% of your time, that is your probability of not stocking out. And mathematically, you're writing that as your inverse of X CDF for PNS. The way you can do that in Excel is by saying your norm.s.dst and whatever k is, and putting that as true. Now, we can also use a fill rate model, and your fill rate is equal to 1 minus your expected shorts per cycle over Q. So what is your expected shorts per cycle? We've already seen that last quarter, last semester. Your expected shorts per cycle is your normal loss function, which we will see how to find that out. Your GQ times your standard deviation of your lead time demand. And I've given you the normal loss function table in your notes. It's table 3 of your notes. And we'll do a couple of examples so you can see how to use them. So let's look at how we can calculate each one of these things. So I said these costs should be functions of your decision variable. So the first one, the cycle stock, is Q over 2. All right? And we know immediately that Q is one of our decision variables, which is how much we have to order. Now, your safety stock is K times sigma X. Now, what is K? K is, as I said, your standardized reorder point. So in Excel, you can calculate your S as the norm dot inverse of your PNS and your mu x and your mu d. So your K is implying whatever your S value is. Okay? So this is, in other words, your standardized S value. Another way of writing it is saying, you can write it more directly, and you can say S minus mu x. So now, instead of writing a safety stock as K times sigma x, you can also write it as S minus mu x, and here you're directly writing it as a function of your when to order, which is your S. Yep? So your pipeline stock is mu x, which is also equal to mu d times mu L, or your average demand times your average lead time. Now we've already seen what order cost is. It's your ordering cost A multiplied by your annual demand divided by whatever Q is. So your ordering cost is a function of Q again. And then once you have all of these, once you have your actually inventories in place, then it's relatively easy to get your cost for each inventory, your cycle stock times your value times your holding cost, and your safety stock times your value times your holding cost, and your pipeline stock is your pipeline stock times value times holding cost. Now, before we go onto the examples, is there anything over here you want me to go over again? A lot of this should already be reviewed. We're only introducing the expected charges per cycle, the S, the K, and the PNS. So those are the three things, and we're going to talk about that both in the example as well as when we do the spreadsheet example using the mathematical program. Yes? K. It is a safety factor. Let me explain what K is. I think it always helps because that's often where most of the time people have a problem understanding this. So this is our distribution of X, which is what? What is X? Sorry? No. Sorry? No. L. That's L. Lead time demand. So what is the definition of lead time demand? It's on average how much demand we have in each lead time. Right? So we look at what our lead time is for each order. We look at how much demand we get during each of those lead times. We take the average of that and we get this distribution. Why do we need that lead time during demand? Because it is that lead time, it's during that lead time when we can actually stock out, right? Because that's the period, that's the so-called risk period. Because when we've placed an order, that's when we've placed the order at the trigger point, right? And at that point, we are only going to get less and less inventory, and our demand is going to increase, right? So depending upon when the order arrives, that lead time demand period is very important. That's why we're looking at the lead time demand graph here. Okay? So, we have an average of lead time demand, right? Everybody with me on that? And we have a one standard deviation of lead time demand, right? So this is our standard deviation of lead time demand. Now we are not interested in this side because we are interested in making sure that we satisfy most of the lead time demand, right? So let's say we want to satisfy 98% of the lead time demand. Yeah? that okay? So the first assumption that I'm making is that lead time demand is normally distributed. Now there's all kinds of disputes in academia about that, but still this is the most robust way of modeling this. So if you accept everything that I've put over here, what is K? If you can imagine that I have the standardized normal distribution that is identical to this, if I can draw it identically, and I say I want to satisfy 98% of this demand. Now for the standardized normal, instead of having mu x, I have a mean of 0, and I have a standard deviation of 1. Okay? So what I have here, so for example at 98%, this is the area under the curve. 98% is the area under the curve up to this point. That's 0.98. Okay? So what is the inverse CDF? The inverse CDF is saying, what is the inverse of 0.98? It tells me what is this point over here, and this is my S. So in order to satisfy 98% of my lead time demand, I must set my reorder point to S. Okay? So that same point corresponds to K over here. That's what K is. Okay? It's the inverse CDF of the standardized normal distribution. This is the inverse CDF of the lead time demand distribution. All right? So K is the inverse CDF of the standardized normal distribution. And S is the inverse CDF of the lead time demand distribution. Okay? Because what I'm doing over here for both cases is I'm just finding 98% of the area under the curve, and I'm saying, tell me what is that point over here. Now, for the standardized normal distribution, we're going to get the standardized value, which is K. Okay? So you use, for example, you use that in your confidence intervals, right? We call it Z over there. Here we call it safety factor, we call it K. But for your prediction intervals, we call it Z. For 90%, what was it? It was 1.282, right? It's the exact same thing. So if I were to take 98% over here, if I was to take 90% over here, and 90% of the curve, then this value would be 1.282. This value on the standardized normal distribution. 98% would be what? 1.645? All right? Or in that vicinity, 1.72 something. So this is what K and S is. All right? Yes? So this is your Z-score. All right? We call it K, we call it safety factor here, but it's really a Z-score.
So it's the same thing.
It's the same thing.
Okay.
Yeah. It's just the nomenclature and the notation in inventory management calls it K. Right? So that you don't confuse it with the other things. Because when we're using equations, we want to have separate items for separate, because we use forecasting in here as well.
Yeah, so you want to have the things separated.
So you want the forecast errors to be different from your inventory. Does this make more sense now? A little bit more sense, maybe? Any other questions? All right. Let's look at a few problems, and it's going to get a little bit easier as you go along. Oh, wait, we have to talk about the surface objective. So, there's two ways in which we can approach the service objective. One is where we use it as a constraint. The other one is where we consider it as a cost. What are the different service objectives? we have the probability of not stocking out, which I told you about already, which is if I have an order, what's the probability that I'm going to stock out during the lead time of that order? That's the next one is the fill rate, which is how much of demand am I going to fulfill from my on-hand inventory, from my balance on hand or on-shelf inventory. So that's my fill rate. And this is the ready rate, which we're not going to use. And again, time between stockouts, which we're not going to use. It's used in certain specialized areas. For the cost minimization approach, we consider what is the fixed cost of a stockout. We say every time we stock out, this is how much we're going to cost us. Okay? And then we put that in the objective function. Or every time we stock out, for each unit that we stock out, there is a certain stock out charge. All right? And for each, so for example, every time we have a stock out, we look at how many units we're stocked out for. It could be because that stock out charge could arise because we have expedite those units to the customer, or because we want to build into it some cost where if we stock out with a certain number of units, then the customer is not going to give us extra business. So whatever that cost is, we're going to say that that cost is going to be part of the objective function. Then also there is the fractional charge, which is a per unit short per unit time. So you can say for every unit that we are short, and every unit that we are short for a certain number of periods, we're going to have a certain cost. And again, that's specialized use. And then we can also have item short, we can have a shortage cost per line item. So last class we talked about the perfect order index. So we see for every single line item, if we were short for any line items, then there would be a cost for that particular line item. And we typically don't use those two in general. So let's look at an example here. So we have annual demand of so much. We have an average lead time demand of so much. We're familiar with what the CVD and CVL is, right? So for TIE, it's the coefficient of variation of demand, coefficient of variation of lead time. The CVD for anything is equal to the sigma over the mu. All right? So we can calculate the CVD as the ratio of the standard deviation over the average. So this is the coefficient of variation of demand and the coefficient of variation for lead time. The ordering costs are $50 for each order. You have a holding factor of 30% for your warehouse inventory and 20% for your pipeline inventory. You have an item value of $75 and you assume that you have 365 days, so you're working 365 days of the year. Now sometimes you can assume that you're working 250 days of the year if you're in a retail environment and you're not operating every single day of the year. You want to make sure that you satisfy 95% of your demand. You want to make sure that 95% of the time, 95% of your orders, you don't have a stock out. You want to make sure that 98% of your demand is met from on-hand inventory. If you have a stock out, then it's going to cost you $300. And if there is a stock out for each unit that you're stocking out, you're going to have a 35% cost of that unit. So if that unit costs you $1, then you're going to have to pay 35 cents in stock out costs if you're stocked out of that unit, right? So these are the parameters of the problem. So let's look at calculating the PNS if 500 units are ordered when the balance in hand is 280. So now we imagine this scenario where the company we are working for, the company that is doing this, currently has a policy of an order quantity of 500 that is triggered when you have 280 units in inventory. Okay? So, where do we start? So our Q is equal to 500 and our S is equal to 280. So what do we need to know? We need to find out our PNS, which is P1. And what do we know about our P1? It is equal to so remember the K is the inverse CDF of P1. So P1 is equal to the CDF of K. Okay? So that inverse works. So let me just put that over. So this is equivalent to say which implies that yeah, this is K. So the CDF of K is equal to P1, which implies that the inverse CDF of P1 is equal to K. All right. So that's in probability. That's in statistical theory. That's just the rule. Okay. So what do we know about K? What do we know about K? K is the standardized value of S, right? So how do we standardize S? To standardize S, we can either go and look at the formula that we saw we can look at this formula here, or anytime you want to standardize any value of a normal distribution, you have to center it, that is, you have to subtract it from its mean, and then you have to scale it. That means you have to divide it by its standard deviation. All right? So when you center it, in other words, subtract it from its mean and scale it dividing by its standard deviation, you get its standardized value, okay, for a normal distribution. We know that S is equal to 280, and we know that the average of lead time demand is equal to 200, right, from what's given to us. If you go back and look at the problem, our average of lead time demand is 200 units. Then we also know that we have a total of 7,300 units of annual demand. Our days per year is equal to 365. So we can calculate what the average demand is, which is 7,300 divided by 365. So our average demand is equal to 20 units per day. So we have our average demand and we have our average lead time demand. So now we can calculate what our average lead time is, right? Because what's the average? It's UD times UL, right? So our average lead time demand is 200. Our average demand is 20. And this gives us an average lead time of 10 units or 10 days. So the reason why we need average lead time, we need average demand, and now we need the standard deviation of demand and standard deviation of lead time is because if you remember from our formula for sigma x, what's our formula for sigma x? It's the average of lead time multiplied by the variance of demand plus the average of demand squared multiplied by the variance of lead time. So we've got the average of lead time, we've got the average of demand. Now what we need is we need the variance of demand and the variance of lead time. So how do we get the variance of demand and variance of lead time? Anybody? We did this in 355 as well. Sorry? No, we can just calculate it. You don't have to look at the chart. What is that? What is standard deviation divided by average? What is your coefficient of variation of demand, right? So a coefficient of variation of demand is equal to the standard deviation of demand divided by the average of demand. So your standard deviation of demand is equal to the average of demand multiplied by this coefficient of variation of demand, which we know is what? So it's 20 times 0.2. So your standard deviation of demand is equal to 4 units. And similarly, standard deviation of lead time is equal to average of lead time, which is 10, multiplied by coefficient of variation of lead time, which is 0.3, which is equal to 3 days. So your sigma x is equal to 10 times 4 squared plus 20 squared times 3 squared, which is equal to 61.319. Times 0.3 is 3, right? So, going all the way back to K, we now have our reorder point, which is 280, minus our average of lead time demand, which is 200, divided by 61.319, which is approximately equal to 1.30. So, now what do we do? So if you go to table 2 of your notes, can I borrow your notes here? Yeah. This one. Can I pull this one out? So, you'll see the cumulative distribution of your standard normal in page 2, table 2 of your notes, which is on page 30. So the 1.3 that we calculated here is your k value. Okay? Now you can go up to 2 decimal places because the table goes up to 2 decimal places. So you can round up to 2 decimal places. This is approximately 1.3. So here you can go down and you can see 1.3, which gives you 0.903. Alright? Which means that your PNS is 90.3 using this current order policy. Okay? So 90% of the time, 90.3% of the time, you're not going to stock out. So in other words, if you have 100 orders each year, 90% or 90 of those orders you're not going to stock out. The remaining 10, there is a very good chance you're going to stock out. Okay? Thank you. Any questions about this? 90% of the time you won't stock out. Because the customer service requirement is called PNS, probability of not stocking out. Okay, so this is your PNS. So from table 2, you will see that it is 90.3%. So how does this target measure against your current target? Against the desired target? You're off by about 5%, right? What the desired target is 95%. So what are you going to do to get that 95%? Yeah, so we'll get there. So that's the question. Also, based upon this reorder point, this S, what is the fill rate? So our fill rate, we also call it P2, is equal to 1 minus expected shots per cycle divided by Q. We also know that our expected shots per cycle is equal to the normal loss function. This is called the normal loss function. That is ESC over Q. And that is multiplied by sigma x. So your normal loss function multiplied by your standard deviation of lead time demand. Now we know what our K is. Our K is equal to 1.3. Now going to your table 3 of your notes. Let me take this again. Table 3 of your notes has got the normal loss function listed over there for you. Okay? And again, you can use this even in your workplace if your workplace doesn't already have these tables over there, it doesn't have a computer or software for it. So you do the same thing, 1.3, and your normal loss function works out to be 0.046. Okay? So your G of your normal loss function is equal to 0.046, We know that our standard deviation of lead time demand is 61.319, and so our expected shots per cycle is equal to 0.046 multiplied by 61.319, which gives us 2.821, which is telling us that every cycle we're going to stock out by about, on average, 2.8 units. So for our P2, it's 1 minus 2.821 divided by our Q, which is 500, which is a 99.4% fill rate. So here you see an interesting paradox. The paradox is that our probability of not stocking out is lower than what we expected, but our fill rate is higher than what we want to set. Question? Multiply k by 0.04. This is a function. So
So that's
G is a function
Okay.
using k. Okay? So G is a normal loss function, and the input into the function is k. No, it's not k times sigma x, it's G of k times sigma x. So G is the function. Okay? So a function is just simply a formula in which k is just one input. Alright? So the formula is very complex. So we are not actually using that formula. So just to represent that formula, I'm just giving you G, and K is just one of the inputs. Yes?
So what did we use when table 3?
We use K because K was an input into the normal loss function. Table 3 gives you the output, what is G of K for each input of K. Okay? So we use 1.30, and then our normal loss function worked out to be 0.046. So we'll continue by looking at how we want to set our reorder point to achieve a 95% probability of not stocking out, and then calculate what our safety stock is. If you want, you can do that at home and see how you fare with that, so that when we do it in class next time, you can ask questions about what difficulties you had, and then we look at some mathematical programs for doing these other problems. All right, I'll see you on Thursday then.